This is our example on slide 35 of our chapter 21 PowerPoint. And here they want us to predict whether each nuclide is more likely to decay via beta decay or positron emission, and they give us 3 examples. So before we start this problem, I want to make sure we're clear on the concept of the N over Z ratio. So N over Z, the number of neutrons over the number of protons, is a ratio that helps us determine if an element is going to be stable or if it's going to be a radioisotope, if it's going to decay in some way. So if you look at slide 34 on your PowerPoint, there's kind of a graph showing basically the valley or belt of stability for certain elements, and that's basically the ideal ratio of neutrons to protons. So for the atomic numbers 1 through 20 are relatively light elements. The ideal N over Z ratio is 1. For little heavier elements, atomic numbers 20 through 40, our N over Z ratio is 1.25 if we want a stable element. And then for Z, even more heavy elements, for Z of 40 to 80, the most stable elements have an N over Z ratio of 1.5. And then once we approach an atomic number of above 83, those elements are no longer stable regardless of our neutron to proton ratio. So, for our example, to figure out what type of decay these 3 elements are going to undergo, just know that if your neutron to proton ratio is too high, the element is going to want to undergo beta decay to become a more stable isotope. And if our neutron to proton ratio is too low, the element is going to undergo positron emission or electron capture. And in this case, we're only choosing between beta decay and positron emission. So for A, our first guy, magnesium 28, some things I need to figure out is number of neutrons and number of protons. So magnesium 28, remember 28 is representing its mass number. That's number of protons and neutrons. So to figure out protons, we'll look at the periodic table. So protons are equal to 12, and our neutrons are going to be 28 minus 12 to give us a total of 16. So from here, we can figure out our N over Z ratio, our number of neutrons over protons. So 16 divided by 12 gives you an N over Z of 1.33. Now, magnesium, we know, has an atomic number of 12. That puts it in the 1 to 20 range. And ideally, the N to Z ratio should be 1. But we have 1.33, which is higher than 1. Therefore, the magnesium 28 is going to undergo beta decay. How do I know that? Because if I compare my ratio of what the element currently is, the N to Z, 1.33, it's larger than 1. And remember, if our N to Z ratio is too high, we undergo beta decay. So your final answer for this problem, for part A, is it undergoes beta decay. For the next one, similar process here. We already know that magnesium has protons. It has 12 of them. And in this case, we're looking at a mass number of 22. So neutrons is going to be 22 minus 12 to give us a total of 10. So to get our N to Z ratio, it's going to be neutrons over protons, so 10 over 12, which is equal to 0.83. Now remember that our Z for 1 through 20, so remember we have 12 protons, that's our Z, 1 through 20 should be 1, but it's currently 0.83, which is less than 1. So therefore, we are going to undergo positron emission because our N to Z ratio is too low. So too low, N to Z undergoes positron emission. Hopefully that makes sense. So that's your final answer for this part. And then finally, for part C, we have MO102, that is molybdenum. So we have a mass number of 102, and if we look at the periodic table, molybdenum has 42 protons. So protons are 42. To figure out number of neutrons, it's going to be 102 mass number minus number of protons, and that's going to equal 60 neutrons. To figure out our N over Z, we're going to take neutrons over protons to give us 60 over 42, which if we calculate that, that is 1.43. So, how does that compare to the stable N to Z ratio for this type of element? So, molybdenum has a number of protons, an atomic number of 42. Therefore, the most stable N to Z ratio, it's in the 40 to 80 range, is going to be 1.5. So, 143 is technically smaller than 1.5, but this one's a little tricky in your textbook or in your PowerPoint slide. If you look at the valley of stability, it's not exactly 1.5 for elements 40 through 80. This one is actually approaching roughly 1.3. So 1.43 is bigger than 1.3. Therefore, the N to Z is too high, and we undergo beta decay. This one is a little tricky because once you get beyond a Z of 20, they approach the numbers that are stated in the slide 34, but they're not exactly equal to that. So in this case, technically, the ideal Z for this element is 1.3. Therefore, it undergoes beta decay because 1.43 is larger than 1.3. So I'm sorry if that is a little confusing. On the ACS exam or any homework problems, I'll make sure to only pick problems that are very concrete in their definition. So there you have it. That's how to determine if something undergoes beta decay or positron emission.